Hello. Very good morning to all. Now I'm going to share my screen. Uh, Let me know. Can you see my screen or not?
Yes, sir.
Yes. Okay. Thank you. Thank you. So let us see. So last time we were discussing about light up. Last time we were discussing about that is the elimination reaction. So in elimination reaction, we have seen this elimination reaction are of different type depending upon the type of group removing from which position. So this elimination, they may be of 1-1 elimination, 1-2 elimination, or 1-3 elimination, and so on. And in that one, we are discussing about 1-2 elimination. So this 1-2 elimination reaction, they are of, or it can be explained by three mechanisms. One, we have learned already E2 mechanism. Second is your E1 mechanism, and third is your E1CB mechanism. You have learned in detail about the E2 mechanism. So it is a one-step reaction, one-step mechanism. It is a one-step mechanism where there is a formation of a transition state. So bond breaking, bond forming process takes place simultaneously, and there is a formation of that is a product, that is a alkene. So you have learned this reaction in detail with respect to that is the definition. Then we have seen general representation. We have seen examples. We have seen mechanism, and in mechanism, we have seen it is a one-step process, and later on we have given the evidence for the mechanism, and also in that one you have seen the Sergep rule, and after that one you have seen the Hoffman rule. So here with this point also we have to explain that is the E1 mechanism. Last time we also discussed what is meant by E1 mechanism. In E1 mechanism, we have seen in general that if suppose in general, suppose you are having a such type of starting compound where there is a presence of X leaving group and there is a hydrogen. It is a substrate. This substrate, when treated with the base, so here what happened, halogen is more electronegative as compared to carbon. So in mechanism we have seen this sigma bond open on the X, there is a formation of X negative. Here X may be chlorine, bromine, iodine, such type of halogen group, or you can take also any other group. Base may be sodium ethoxide, Na plus, O minus, C2H5, or you can take also any other base. So in even mechanism what happen, the halogen atom directly attach to the carbon. That carbon is called as alpha carbon. That carbon is called as alpha carbon. So this carbon is a alpha carbon and this carbon is a beta carbon. So this sigma bond open here and there is a formation of a corresponding that is a carbocation. So in the first step there is a formation of a carbocation. Here you are getting a such type of a carbocation. So this C becomes a C positive. So it is a carbocation. Further, this carbocation it react with the base. So in the first step, there is no use of this base. So here only the sigma bond will open on X. So this base do not abstract. So even though if you don't write this base, it also work, right? So here we will not write in the first step, we'll write in the second step. So in the first step only, there is a formation of carbocation, and in the next step, there is a use of this base. So here I take base in particular that is Na positive, O negative, and C2H5. So this base abstract the proton. So this H is abstracted by the base O minus. At the same time, as this abstracted base, so this sigma bond will shift here and there is a formation of a carbon-carbon double bond. So there is a formation of a carbon-carbon double bond between the alpha carbon and beta carbon. Here is alpha carbon and beta carbon. This is alpha carbon and beta carbon. So there is a formation of corresponding alkene. Right. So you get corresponding alkene. And there is a removal of, here if I take a base ethoxide, this H react with the base and there is a formation of corresponding ethyl alcohol C2H5OH, right? So in this way, we have seen this mechanism. It is a two-step process. So first step is the slow step. In this case, the first step is the slow step. It is the RDS step, rate determining step. And second step, where there is abstraction of proton, is a fast step. So it is a slow step and a fast step. So we can say the rate of reaction is directly proportional to the concentration of substrate. The rate of reaction is directly proportional to the rate of a substrate. Why? Because only substrate is involved in the RDS step and returning step. What is the rate of reaction? Rate of reaction depends upon the concentration of that is the substrate. Here only one molecule that is a substrate is involved in the RDS. So you are having a such type of a substrate and here you can write that is a substrate. We can remove the proportionality constant and rate is equal to K1 substrate. Okay, so this is the mechanism of the reaction that you have learned already. Near about, I think near about 3 times we have repeated this mechanism. Now, same thing we have to learn with the example. Last time we have taken this valency is satisfied by the ethyl. Now here I will take ethyl group. And let us see the mechanism of the reaction. So this valency, suppose if I write here that is the CH3, right, methyl group, then this is H. I have replaced the valency by H, and here we can replace by any alkyl group. So we have now writing its example. So itself in the representation, you should know how to make its example. And if you know the generalization into example and example into generalization, then them ask, or you can write any example. So try to make every reaction in general, and how to make that in general into the in particular means in the example. So here what you have done, I have all the hydrogen by the methyl. Even though you can put here also methyl group, even though this methyl can be ethyl also, right? Now, same thing I'm going to write. I am not doing anything. Only I am going to replace this by the methyl group, right? There is also methyl group and also methyl group, right? Now, in this case, what happened? Here is alpha carbon and beta carbon. At the same time, also there is a presence of a beta dash carbon. Here is a beta dash carbon, beta dash, right? Actually, it's a beta, but only to just differentiate between these two, I have written it is a beta dash. The carbon atom directly attached to the functional group is called as the alpha carbon, and the carbon atom directly attached to the alpha carbon is called as a beta carbon, and the hydrogen atom directly attached to the beta carbon is called as a beta hydrogen. Right? So one of the required condition for the this beta elimination, we can say E2 elimination, is the presence of a beta hydrogen. But here also there is a presence of a two beta hydrogen. So here is the beta and a beta dash. So if you replace this beta, then you are getting here CH3, again CH3, here also there is a CH3 and CH3, right? Here CH3, actually it is a H. I have taken here CH3. So replace this CH3 by H, CH3 by H, right? So here also H. So you are getting how many alkyl groups are there? 1, 2, 3. So it is a trialkyl. It is a trialkyl. Trialkyl. You are getting this compound. But again, there is one more possibility is that, so this carbon is a beta. It is also beta, right? So there is a presence of 1, 2, 3. Three beta carbon atom. There are the three type of beta. Even we can write also beta dash. Here also beta dash. So it is a beta dash, double dash. Right? It is a beta double dash. Right? So here, we have seen in this case the mechanism, that is there is a formation of a trialkyl alkene. Trialkyl alkene. We are having three type of beta, beta dash, and beta double dash, right? So we can replace this beta and beta dash, but both are same. Both are same. So instead of writing beta double dash, even though you can write only beta dash because both are same. So here is a beta and a beta dash. Now we can also replace this beta dash and can get also one more compound. So let us see how there is a removal of a beta dash. So what we can do, we can replace this one of the hydrogen here, and there is a formation of corresponding compound. So there is an introduction of one more carbon double bond. So here you can get, that is here is a CH3, here is a C, here is H, already there is H, here is the H, now here is the H. We have to replace beta dash. So this CH3, these are alpha carbon, and there is a removal of hydrogen, that is a beta dash. So it is a beta dash, right? So replace this alpha beta dash hydrogen, and you are also getting corresponding alkene. corresponding alkene. But in this case, you'll find that 1 and 2, there are the two alkyl group directly attached to the doubly bonded carbon atom, that is the alpha carbon atom. So it is a dialkyl substituted alkene. Dialkyl substituted alkene. Now here, let me know which is a major compound, either compound number 1 or compound number 2. Which is the major alkene, number 1 or number 2? You have to tell me that is which is the major, number 1 or number 2, and why? Yes, first. Yes, which is the major? Srushti. Yes, tell me first. Ankita, which is major, first or second? First is a trialkyl and second is a dialkyl. So which is the major compound, either first or second? Can you hear me? Yes. Whether I am audible?
Yes, sir.
Okay. So is the major compound first or second?
First, sir.
Trialkyl, because there are the three alkyl group directly attached to the doubly bonded carbon atom. And second is a dialkyl, because only two R group directly attached to the doubly bonded carbon atom. So in this case, the one compound, first compound is a major. Why? Because the elimination is governed by the Sergev rule. What is the Sergev rule? Sergev rule, here you are having a major compound. You are having a major, right? Major compound. And here you are having a minor compound. Minor compound. So the elimination is governed by the Sergev rule, right? So this is the mechanism of the reaction where the elimination takes place. So we have seen that is the definition, general representation. We have taken example. Last time we have taken already one example, and we have seen the mechanism of the reaction. So it is a two-step process. It is a two-step process in which number one, step one, there is a formation of a carbocation. Formation of a carbocation. Formation of carbocation. So you can write also separately, there is a formation of a carbocation. Step number one, this is step number one, formation of a carbocation. So you can take also another example and you can write the same mechanism. And second step is a abstraction of proton. Step second is a abstraction of proton or formation of alkene. So it is a two-step process. In SN1 reaction, there is a formation of carbocation. So it is just similar to your SN1 mechanism, because in both reactions there is a formation of carbocation. So it is just similar to your SN1 mechanism. Only second step is different. When base act on the carbon, it acts as a nucleophile, and there is a SN1 mechanism. And when it attack on the hydrogen, it is a E1 mechanism, and there is a formation of a E1 mechanism and formation of alkene. Right? So here, if it have one only beta hydrogen, you get only one compound. If you are having a two beta hydrogen, then you are having a two compound. But with the major is governed by the Sergev rule. So depending upon the substrate, you are having that type of the compound. So here we have seen the mechanism of the reaction, right? The mechanism of the reaction, right? Any doubt? Yes, no doubt. It's clear to you the mechanism of the reaction? Yes. Is it clear to you mechanism of the reaction?
Yes, sir.
Okay, right. So let us see. Thank you. So let us see the next point. The next point is the evidence for the mechanism. Evidence for the mechanism. So let us see. So we have to see evidence. evidence for E1 mechanism. Evidence for the E1 mechanism, right? So in evidence, what you have to see, the mechanism takes place through the formation of two steps. Step one, formation of carbocation. Step two, there is a formation abstraction of proton, and you get corresponding compound. So step second, you'll find that there is a breaking of a CH bond. There is a breaking of a CH bond, right? So this H is abstracted by the base. So CH bond breaking takes place. In this case, what happened? The CH bond breaking takes place. So you have to explain whether the CH bond breaking takes place in the reaction or not. And it can be explained by kinetic isotopic effect. Kinetic isotopic effect. So let us see. First evidence, kinetic isotopic effect. Kinetic isotopic effect. So in kinetic isotopic effect, what we do, we have learned this kinetic isotopic effect also in the aromatic electrophilic substitution reaction, where we explain whether the CH bond break in the RDS step or not, rate determining step or not. If it break, then the rate of reaction will be different. If it do not break, then rate of reaction will be the same. So let us see the example for this one, kinetic isotopic effect evidence. So in this case, what you have to do, we have to take an example. Suppose number A, in this one, there is a carbon. Here is your CH3. Here is a CH3, CH3, and here is a, suppose if I take here Cl, chlorine. So this carbon is alpha, this is your beta, right? This carbon is alpha, here is all are beta, right? Beta, here is also beta, and here is also beta, means all carbons are same. This beta carbon contains hydrogen, so it is a beta hydrogen. So this reaction, when treated with a base, you can take any base, Na plus and O, C2H5O, sodium methoxide, NaOH, KOH. So you can take a base, and we have to find out what is the rate of reaction. Now you know, when it followed by the E1 mechanism, then the sigma bond between the C alpha and Cl, it undergo breaking. So Cl get negative and C get positive. So there is the formation of a carbocation. And further, one of the hydrogen from the beta, it will shift on the sigma bond, and there is a formation of double bond between the alpha and beta carbon atom. So here I am writing one more hydrogen only, right? So instead of writing CH3, I write here CH2 and H. You can take any methyl. I have taken here this methyl. So this sigma bond, I am writing a direct reaction. I am not writing a stepwise, right? So there is a formation of a corresponding alkene, and you are getting corresponding alkene like this one. That is a CH3. Here is the carbon. Here is a CH3, right? And you are getting corresponding alkene. So in this case, you find out its a rate of reaction. Rate of reaction is equal to KH. KH, because all are the hydrogen. Now we make a some modification, and we'll see the same example. We what is the name of this compound? Tertiary butyl bromide. Tertiary butyl. Here is the chloride. Tertiary butyl chloride. Every time try to write the name of every compound. It is isobutene. It is your isobutene. Now in the second example, what you do? Here is a substrate, here is a Cl, and this hydrogen, they are replaced by the deuterium. The hydrogens, they are replaced by the deuterium. So here is a D, means the hydrogen is replaced by D, CD3, 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 right? So here we can say deuterated tertiary butyl chloride. So the name of this compound is deuterated tertiary butyl chloride. Now this deuterated tertiary butyl chloride, also we can write one of the D here, right? So instead of writing D3, I write here that is a D2, and there is a one more D, right? Further, it undergoes elimination in the presence of base. We take the same base, Na plus, O minus, and C2H5, and we have to find out what is the rate of reaction. So in this one, what happened? The bond between the C alpha and Cl undergo breaking, and the bond between the C beta and D undergo breaking. So here, this is your alpha carbon, this is your beta carbon atom. So this sigma bond break, carbon becomes positive. This sigma bond break, formation of a double bond, and you are getting corresponding compound like this one. C, here D3, D3. Here is the D3. Further, you are having alpha carbon, and there is a formation of a carbon-carbon double bond. So you are having corresponding compound like this one. So here is a D3 and here is a D2. So you are getting a deuterated isobutyl. You get such type of compound. Now we have to find out what is the rate of reaction. So experimentally we find out a rate of reaction, and it is found that the rate of reaction, we note it as a KD. KD. So here the rate is a KD, right? And experimentally it is found that KH is equal to KD. KH is equal to KD. So what it indicates? It indicates that the CH bond breaking is not involved in the RDS step. The CH bond breaking is not involved in the RDS step. So when KH is equal to KD, in that case, the bond between the carbon and hydrogen do not break. So CH bond breaking is not involved in the RDS step. So it is one of the evidence. And what our mechanism tells? Our mechanism tells us that here in the mechanism, in the slow step, there is no breaking of bond between the C beta and H. But in the fast step, there is a breaking of a bond between the C beta and H. So it is a do not obey kinetic isotopic effect. So here we can say that here is a no kinetic isotopic effect. In this case, there is a no kinetic isotopic effect. So in this case, there is a no kinetic isotopic effect, right? So it gives evidence that CH bond breaking do not break in the RDS step. So there is a one evidence. Let us see the next evidence. In next evidence, we have seen that there is a formation of a carbocation. Right? There is a formation of a carbocation. So next evidence, we have to give structural effect. Structural effect. So in structural effect, we have to check whether the structure of substrate, whether it affect on the reaction or not. Now, suppose if you take such type of substrate, for example, tertiary butyl chloride. there is a carbon, tertiary butyl chloride. We'll take in, here is a carbon, CH3, then CH3, here is also CH3, and here is a Cl. It is a tertiary alkyl halide, and it is a tertiary alkyl halide. That is the tertiary butyl chloride. In the first step, we have seen that in the slow step, in the E1 mechanism, this sigma bond break, and there's a formation of carbocation. So you are having a CH3, here is a CH3, here is a CH3, and C positive. Further, if you take such type of substrate, CH, CS3, and here is a Cl. Again, this sigma bond break, it is secondary, it is a tertiary halide, it is a secondary halide. It is your secondary halide. So in the secondary halide, what happens? Again, in the RDL step, slow step, there is a formation of a such type of a carbocation. Here is a H, and here is a CH3. So you will get such type of carbocation, and you get such type of a secondary carbocation. Further, if you take such type of a starting compound, that is the Br, so it is alpha carbon, beta carbon. This sigma bond will open in the slow step. In the RDS step, what we get? We get corresponding formation of a such type of carbocation. And so, what happened is the secondary carbocation, third is the primary carbocation. We have learned the stability of a carbocation. The stability of carbocation we have learned in the nucleophilic substitution reaction. So if you see the reactivity in E1 is that tertiary alkyl halide more reactive as compared to secondary alkyl halide as compared to primary, as compared to secondary alkyl halide, as compared to primary alkyl halide. So here there is a formation of a carbocation takes place. If suppose if you are having formation of a more stable carbocation, that is a tertiary carbocation, then the rate of reaction will be the faster because it is the more stable. Every species want to give the stability. So I give tertiary carbon, it is the more stable as compared to secondary, as compared to primary. So the reactivity will be in the sequence, that is the tertiary, then the second, and then primary. So here the structural effect, it shows that the tertiary alkyl halide, it can undergo easy E1 or SN1 mechanism, because in both SN1 and E1 the formation of a carbocation. More the stable carbocation, more is the rate of reaction. So as we move from primary to secondary, secondary to tertiary alkyl halide, in that case, first step is the formation of carbocation. As there is the formation of more stable carbocation, so there is an increase in the rate of reaction from secondary to tertiary alkyl halide. Why? Because the formation of more stable carbocation. Right? So this is about your rate of reaction, how the structural effect tells us that there is a formation of a carbocation, primary, secondary, and tertiary. Right? Now let us see the next evidence, that is, suppose C, rearrangement. We have seen that just now step is a formation of carbocation. In E2 mechanism, the bond forming process carbocation. So if structure permit, then reaction. Forming such type of compound, right? So you are having such type of formation of carbocation, and let us see how it gives corresponding formation of a product. Suppose it is 9 10, it required again some more 10 to 15 minutes. Let me know whether you got this point or not. What we have learned? We have learned E2, E1, E1 shipping. In that one, we have seen E1 mechanism. In E1 mechanism, there is a formation of carbocation. Hello. Formation of carbocation. 1 minute. I think Hello. Yes. Can you hear me? मेरा आवाज आपको आ रहा है?
Yes, sir.
Yes, sir.
And can you see the screen?
Yes, sir. Yes, sir.
Screen दिख रहा है आपको?
Yes, sir.
Okay, right. So here we have seen that is the formation of carbocation first, and this carbocation, there is an abstraction of proton, and you get the alkene. Then we have seen evidence for the mechanism, no kinetic isotopic effect, and next is the structural effect. So next one of the evidence, that is a rearrangement. So you know, in the first step there is a formation of carbocation similar to your SN1 mechanism. If structure permit, if suppose there is a formation of primary carbocation may be converted into the secondary carbocation, and maybe also convert into the tertiary carbocation, and further it undergo, that is the corresponding abstraction of proton, and you get corresponding alkene. So this point will say later on. If you have any doubt, you may ask. यदि आपको कोई डाउट है तो आप पूछ सकते हो. If you have any doubt, you may ask. Any doubt? Okay. Thanks to all. I think we should stop here, right? So you can leave the meeting, and you can join the next lecture. Thanks to all. Thank you.
Thank you, sir.
Thank you, sir. Thank you. Thank you. Thank you. सृष्टि समय आ गया आपको? सृष्टि, are you getting?
Yes, yes, sir. Yes.
Okay. साक्षी समझते का?
Yes, sir.
Vishal, are you getting?
Yes, sir.
Very good. Very good. Try to read at your home. So, thanks to all.